Good morning.
I just will, we cannot see Andy, so I don't know if Andy wants to turn his video on.
Okay. Working on it.
Well, good morning, good afternoon, and good evening, everyone. Welcome to this morning's keynote. My name is Raj Chana from RBC Royal Bank of Canada, and it is my pleasure to introduce Andy Bechtolsheim for the keynote today. Andy Bechtolsheim is the Chairman, Chief Development Officer, and co-founder of Arista Networks. Previously, Andy was a co-founder and chief systems architect at Sun Microsystems, responsible for the next generation server storage and network architectures. Andy received an MS in computer engineering from Carnegie Mellon University in 1976 and was a doctoral student of computer engineering at Stanford University from 77 to 82. He has been honored with a Fulbright Scholarship, the Stanford Entrepreneur Company of the Year Award, the Smithsonian Leadership Award for Innovation, the EY 2015 US Entrepreneur of the Year Award, along with Jayshree Ullal, and is a member of the National Academy of Engineering. Without any further ado, Andy, please take it away.
Okay. Do you see my screen that should say Ethernet Geek and beyond?
Yes.
Okay, and maybe I can make it even bigger. I don't know. Does this work? Does it show the full screen now?
Yes.
And you got my next slide?
Yes.
Perfect. Okay. So I want to discuss everything from chip level interconnects to rack level, data center, co-packaged optics, pluggable optics, DCI, and so on, from the inside out. So I'm going to start at the chip level. And obviously the hot topic these days, and one of the most important developments along the Moore's law curve, is multi-chip packaging, where the ability to integrate different kind of devices on a single package substrate is going to be very important going forward. Now, this has obviously been going on for some time. A lot of the cell phones chips that have to be miniaturized do this today. At the higher power level, the ability to interconnect, we call them high density chips or high I/O bandwidth chips. There's of course this challenge of how do you connect these chips to each other, and fundamentally one is looking for ways to get an enormous amount of bandwidth between these chips. Work on this area has been going on for the last 20 years. Recent examples are the Intel embedded multi-die interconnect bridge, which is otherwise referred to as a 2.5D technology, and vertical stacking, which is referred to as a 3D technologies. But the most important thing here is that this does enable fundamentally new densities at this chip component level, chip packaging level, that turns what used to be called the system on a chip to sort of a system on a single package. Now, to really advance this going forward, in a multi-vendor kind of situation, there will have to be standardization of these chip-to-chip interfaces. Intel proposed the advanced interface bus, which is one good example. There's obviously memory interfaces, HBM memories today, full-size SRAM dies, various I/O chiplets. The ultimate limit here is arguably the thermal power dissipation, like how much power can one dissipate on a single package. Historically, people have tried to keep power level on single packages down to a few hundred watts. I think the current wisdom is that perhaps up to 1,000 watts per package can be dissipated with conventional means. And there are also new developments here like diamond substrates that could bump up this limit significantly. Now, the other ultimate limiting factor is how much I/O can we get off this chip, the multi-chip package. And the current speed for SerDes that's in production is 100 gig. It's actually 112 gig, but I'm referring to the payload kind of speed, the round numbers. And there's lots of development going on 200 gig SerDes, which should show up in the market in the next few years. There are chips today that have up to 512 SerDes, and there are some vendors who are trying to push this even higher. So realistically today, you can build a 51.2 terabit chip with 512 gig SerDes, or a 102.4 terabit chip with 512 200 gig SerDes, and perhaps even higher. So the speed limit, which I think there was a perception was in the 100 gigabit range, is definitely moving to the 200 gig per lane. And this applies to both optical direct modulation and electrical lanes here, since they're driven by the same kind of SerDes technology. Now there's this other question of when does the power for this I/O, the electrical power required to drive the I/O, exceed the available power on the chip? And there was some discussion a few years ago that this may be as early as in the 25 terabit range. This is a slide from a DARPA project called the PIPES project, where the little triangle there, the red triangle, is where it gets so hot that you're burning all the power on the I/O and you no longer have any power for the payload. Now, arguably, this was pessimistic, and I took the liberty to correct this slide based on the current sort of information available, and it looks something like this, except I can no longer advance. Let's see what happened here. Okay, let me try to stop sharing here and see if I can restart. Except this doesn't want to do anything now. I'm terribly sorry for the technical disruption here, right in the middle of this very hot topic. I may have to.
Did we lose Andy?
He'll be back, I'm sure.
Yeah, was just checking to see if it was me. Thanks.
Raj, sorry, my internet connection seemed to have gotten disrupted here. Can you hear me again?
Yeah, you're back now, Andy.
Sorry, and where did this drop off? Like which slide? Because I don't actually know when it stopped, because I thought I was still on, but
It was the DARPA PIPES project.
Okay, let's go back right there. And DARPA, of course, has done invaluable work advancing all kinds of technologies over the years. So let me see. So it was that slide, right?
Yes.
So starting a few years ago, the perception was that the electrical power from the required for the I/O, for a chip function, would exceed the total power budget as little as 20 terabits per chip. This is arguably not the case anymore. So the current value for this is at least 100 terabit, if not in terms of the total electric power, more closer to 200 terabit. Of course, if you do want a petabit per chip I/O, there's no solution available for that today. but the conventional way of building systems, which is an electrical I/O from the chip package, can certainly be scaled to much higher power levels, which is the kind of chips people are now working on for the 2025, 26 generation. And in terms of co-packaged optics, it is true that these multi-chip modules can certainly integrate optical components. In fact, because they're different dies from different technologies, there's no limitation to that at all. Unfortunately, or however, I should say, the current state of co-packaged optics solutions available today does not really offer higher shoreline density or lower power consumption than a comparable electrical I/O. So there is actually not any particular advantage to do this today, although I'm not saying this couldn't be improved in the future, but as of today, this has not been achieved. And there's other problems related to running I/O of chip packages, including, where does the optics go? Attaching fiber means you either have a whole bunch of fiber sticking out, or you need some very high density fiber connectors that haven't been developed yet, or you would have some way to interconnect the chip with polymer waveguides directly to a PC board that has these waveguides. People are looking at all of this, but none of this is in production today. The other factor here is one will need much, much more reliable optics. Basically, the failure probability of lasers today is several orders of magnitude away where it would need to be from achieving a system with thousands of lasers. And then that relates to the third issue, which is from a overall reliability, manufacturability, and serviceability model. You don't want to replace a very high performance, high powered system just because a laser has failed. So going beyond the chip now and looking at the motherboard, the chassis, the rack level interconnectivity, the existing electrical I/O SerDes, which have different designations, as you know, like VSR, MR, LR, and so on, work perfectly well over centimeter up to meters, inside a large chassis, or even in a rack, multiple meters with twin-X copper cables. And these solutions are well proven. I mean, they're very reliable, very highly manufacturable, and so on. And so at least in my view, the connectivity of PCI Express, CXL, any kind of Ethernet within the rack will most likely continue to be copper-based, just because it's so cheap and it works well. And it's actually also fairly low power. But clearly, once you get beyond the limit of copper, wherever that limit is, it may be 2 meters in a 200 gigabit twin-X cable, you do need optics, and this is obviously where optics has no competition. So now turning to the challenge of interconnecting all these servers in a data center, and here's some pictures from Google of their football size data centers in Oregon. The challenge is the bandwidth demand in these cloud data centers has been growing at a rate of 50% or more per year, and the network power per bit has only declined, at roughly half that rate per bit, which does imply that the amount of power being used up by the network, including the optics, is growing at an unhealthy rate. Now, there are, of course, the standard silicon process technology improvements ahead. The current silicon generation for networking is 7 nanometer. The 5 nanometer chips are in design. Some of them are in the lab. The 3 nanometer generation is beyond that. And there's a very significant power reduction, at least on the digital side of the logic, between 7 to 5 to 3, roughly a factor of 2 over the course of just a few years. So that's predictable, and that will definitely happen for sure. And that allows us to forecast the power per bit, or picojoule per bit, for the next 3 generations of switch chips, the current one being 25.6, next one 51.2, and the one beyond this is 102.4. So my prediction, at least here, is it will be coming down by a factor of 2 per bit, or it's still doubling in power. But that's sort of what the technology is predicting. The going down to the optics now. So if we break down the DSP, which is the function that takes the SerDes in and drives the optical element, the drivers that may be required, the TIAs, the lasers, and there's DC to DC converters inside to regulate all this. Again, this is expected to be a factor of 2 lower. And this applies to both what we would call client optics, which is the optics that are available for data center or being used for data center interconnectivity, and the future and the longer reach optics for DCI to DCI data center interconnect. So summarizing this sort of power situation here, it is improving roughly a factor of 2 for every 2 process generations. And this is true for the optics as well. And there is a path towards, call it 11 picojoule per bit optics in this time frame. But it's, we need more. And this is where, again, back to co-packaging and the question of, are there other ways to reduce power that would help? Now, co-packaging, as you may know, is a work in progress. A lot of effort has been spent by many companies and many contributors to make contributions to the OIF, to standardization, prototype development, demonstrations, and so on. It's also clear that there's a lot of challenges here, and they're all well understood. They include laser power, optical losses, connector issues, manufacturability, and so on. But going back to the original goal, which is to have less power, there was somewhat of a, I would say, surprising development here, which was the original motivation behind CPO was, quite frankly, to reduce the electrical power by changing the electrical interface from a high power SerDes like LR, which is the standard SerDes on chips today, to a much lower power SerDes that would just be strong enough to drive the co-packaged optics on the multi-chip carrier, and then go optical from that chip to the front panel on electrical power saving. Now, this assumed, of course, that there was such a low power SerDes, otherwise known as an XSR. This is the ultra short reach, few centimeter reach SerDes between the switch chip and this optics TAP, instead of this high power SerDes that's used today. Now, the problem is this actually didn't happen. The XSR SerDes would have required a full, dedicated 5 nanometer tape out for both the switch chips and the DSPs, and there just hasn't been the economics there to make that happen. Instead, what the silicon vendors have done is they designed what I would call a lower power VSR SerDes, which is not as low power as the XSR SerDes, but it still was quite a bit lower power than the original LR SerDes. And that SerDes is in fact achieving at the wall plug level for 51.2 chip a 200 watt power saving, not quite the original 20%, but maybe 15%. And what this looks like on a sort of a graph here, the LR SerDes at, call it 6 picojoule per bit, the VSR SerDes at roughly 3 picojoule per bit, and the XSR SerDes, which was projected to be 1 picojoule per bit, but has not been implemented. And that is the power reduction. What we're looking at today is the green column. Now, the green column, of course, works perfectly fine for co-packaged optics, but it also leveled the playing field between the co-packaged optics and what you would call conventional pluggable optics modules, because you can, in fact, use that same VSR channel to drive a pluggable optics with what's called a fly-over copper cable, which is a way to reduce the electrical losses on the PC board. So the net result of this is that the power today is actually identical between a co-packaged optics solution that uses the VSR channel on the module versus a pluggable solution. Worse than that, and I'm sorry, this is what it looks like with these flyover cables. There's many companies making this. This is a image from a company called Samtec. But there was another problem here, which is to achieve high reliability for co-packaged optics, people have adopted the notion of an external light source, basically a pluggable module that's on the front panel that can be replaced if that laser in that module fails. So that is the module that injects the power from the laser into the co-packaged optics modulator, and then it comes back out to the front panel. Unfortunately, there's additional coupling losses between that light source and the modulator and the front panel compared to a conventional pluggable solution, which actually requires additional laser power and thus increases the power. So this is a comparison between a conventional pluggable optical module, where there's essentially one interface from the, it's all embedded inside the module, compared to an external light source where there's a connector at the light source level, at the CPU level, and another connector from there to the front panel. So you have somewhere between 2 and 4 connectors compared to, call it, 1 connector. And the connector losses are in the range of, like, call it 0.6 to 1 dB, depending on worst case, whatever assumptions. And you most likely also need expanded beam connectors to avoid the issue with dust contamination, and the expanded beam connectors do have higher losses than conventional single mode connectors. So the combination of the splitter and the polarization losses between 0.6 to 1.2 dB per connector, and by the time you have these additional connectors, you end up somewhere, I would say, roughly 2 dB extra loss on the optical side, which increases the laser power by 50% compared to a pluggable optical module. And that's a problem, certainly. Now, there's other ways to reduce laser total power of the solution. One of the better ideas is to eliminate the DSP completely and to use the SerDes. This would be a very special SerDes on the switch chip to directly drive the optics. So this is not the XSR SerDes, but more enhanced SerDes that is optimized for driving optics. And that would certainly eliminate the DSP completely, which would result in power reduction. But it's basically very hard to reduce the power of the existing proposed solution that uses ELS and conventional VSR channels. There's other ideas on alternative modulation technologies, which would have lower insertion losses on the modulators, but those are not in production today. Now, there's other problems with CPO. There's reliability, serviceability, manufacturability, testability, and even business model issues. Let me just touch on some of them. In my honest opinion, the solution will require expanding beam connectors for the simple reality that you can't have a single dust particle resulting in a return of a complete 51.2T switch. And there's dust in data centers, and dust will find its way inside these products. There has to be very intensive or very well-designed internal testability potential, because without this, you cannot actually even manufacture these units because you don't know if they work or not, right? And the final one is there has to be a serviceability model that works at scale, and it's just not practical to remove complete RMA switches. This is a slide on, oops, I'm getting blocked again here, sorry. Let me see what happened here. Oops, now it works. So from purely from a testability standpoint, it has to be that the manufacturer can verify that all the optical ports work at the system level during manufacturing. This requires some type of internal loopback, and the idea would be to fault isolate conditions between the CPU optics, the fiber, and the connectors. This is also required to support field serviceability, because there has to be a way to distinguish whether it's an external fault or an internal fault. And the loopback would have to be integrated, of course, in the optical structure itself. But the summary here is that CPO is actually not required for either 51.2 or the next generation 102.4, because the problem can be solved with pluggable optics, which is just far easier to deploy and don't have any of the design serviceability or manufacturability issues. And I think that the fundamental problem has been that the solution that's available today is just not saving power over pluggable optics. But there are ways to save that in the future. So I'm not saying it's doomed, but we do need lower power solutions to make that more interesting, certainly. Now, other ways to reduce optics powers, 3 nanometer DSPs will save power. Lower power SerDes designs are possible, and people are working really hard to reduce the power of the underlying SerDes IP And so we should not bet against that. And finally, there are these lower power optics modulators in different technologies that are fundamentally lower insertion loss and would reduce the power of the laser. So lots of innovation potential ahead, 200 gig optical lambdas, better laser sources, lower coupling losses, lower loss modulators, work in active gain materials. And I think a realistic goal here for 2025 is to get down to roughly half of what's possible now, basically in the range of 5 to 6 picojoule per bit. And this is a combination of all these technology improvements between, it's really important to eliminate basically optical losses, coupling losses, having more efficient lasers, and reducing modulation losses. Now, the benefits of this apply equally to co-packaged and pluggable modules. So the underlying optics technology between co-packaged and pluggable is identical. So all the advances in optics apply to both technologies. And arguably, pluggable optical modules have the advantage that they're decoupled from the underlying switch platform, meaning as soon as there's an advance on the optics that can be shipped, you can plug it in, and you don't have to wait to synchronize that with a release of a new switching system. So bottom line, the industry needs to focus on the combination of both power reduction and time to market for all of these technologies, from the silicon to the high-speed optics to the better modulators. And ideally, of course, one can line up these technology transitions at the 51.2 and the 102.4 level. But the most important thing is to avoid time to market risk and risk factors that are just hard to predict how long it would take to solve the problem. And just as a reality check here, to develop any kind of new optics, whatever it is, you're talking 2 or more years from the time you have a fixed specification. I mean, this involves, chip level design, going through the fab, the silicon photonics developments. It's not easy to bring new optics to market. There's many vendors spending a fortune in terms of R&D to advance the state of the industry, and it is progressing. It's just, it's not, there's no magic wand here to make this happen faster. And people do need to have clear targets in terms of both form factors, power, dissipation, and the specifications, the optical specifications, to achieve a shipping product in the 2-year time frame. And my system is stopping again. I'm not sure why it keeps doing this. Can you still hear me?
Oh, yes.
Yes.
Okay. Sometimes it just doesn't advance. Let me see if I can. It's just really odd. Okay. So realistically, a 51.2T switch, which is, in design now, will be in the lab next year and shipping in 2023, will look something like this. There's 64 800 gig plugs. Each 800 gig plug, of course, can support 2 400 gig or 4 200 gig or 8 100 gig interfaces. So this is a lot of bandwidth in a very compact and a very cost-effective package. But there's no invention required, to get this kind of product to market. In fact, the 800 gig optics that would plug into here are available in early quantities today and are in optics qualification today, and they will be in volume production before this product even is in the market. And again, it doesn't quite let me advance here. So I'm not quite sure why this happens. Let's see. Yeah, so the other thing that's happening here at the silicon level is simply the transition of the SerDes speed. Most of the silicon shipping today is still 50 gig PAM4. That's shown in the yellow kind of color here. The blue color refers to the 100 gig SerDes speed, is just in the lab right now, but will be in early production next calendar year, and in much higher volume production in 2023. The analyst forecasts are that by 2023, and this is the 51.2T chip generation, the majority of the bandwidth shipped will be based on 100 gig SerDes. And we certainly believe that's the case. But this is how quickly these transitions happen, because it's basically the easiest way to increase system performance, increase system capacity, and reduce cost per bit, is to increase the speed per SerDes. And then somewhere in the 2024, maybe in the 2025 timeframe, in green, is the first time the 200 gig SerDes will show up in the silicon and be hopefully in the market. So there's another transition coming ahead. But between 2022, 23, and beyond, the 100 gig SerDes will be the vast majority of the volume of switching chips shipped. And this is also true for InfiniBand and other technologies that share the same SerDes and optics technologies. And again, my screen is not advancing. Okay, well, this is another way to break down the previous chart. This is on the, just looking at the optics now, and the vertical scale, lots of, like, millions of optics modules shipped. So the 400 gig optics, which are just ramping now into full production, are likely to peak, by 2023 and then actually decline, whereas the 800 gig optics will kick in 2023 and then take over very, very quickly. On the 800 gig optics modules, there's lots of different technologies here. Starting at the top, 800 gig ZR, which is the next generation data center interconnect technology, is in design and is likely to see silicon as early as next year and productization in 2023 in the timeline of the 51.2T generation. There's also a use case for that, call it either CR Lite or just LR, for the 10-kilometer data center range or building to building range where people are running out of fibers and they want to use multiple lower cost 800 gig DWDM between buildings. Then there's the 200 gig PAM4. So 200 gig at the optical level will actually show up before the switch electrical interface, and maybe in the market as soon as 2023, certainly by 2024 in volume, and has the advantage of fewer lasers, lower cost per bit. Now, from a reach standpoint, those modules will be focused on the data center reach, 1 to 2 kilometer, and that's true for the DR4, the 200 gig as well. And then there's the existing 100 gig lambda optics, which can go all the way up to 10 kilometers. And there will be 100 gig DR8, which is 8 parallel channels. The dual 400 gig FR4 is most likely the highest volume. Dual LR4 up to 10 kilometer, and the version that can do 8 channels of 100 gig up to 10 kilometers as well. And then the VCSEL people haven't given up either yet, so there will be a VCSEL multimode fiber solution that may reach 50 or perhaps 100 meters, but no more than that. So lots of different optics technologies that all plug into the same kind of port on the switch, and the customer can choose whatever they need. It could be aggregation of 100 gig, could be aggregation of 400 gig, 200 gig, or 800 gig native, or 800 gig data center interconnect, all supported by the same product. This is an early version of such a product in our lab, in testing out different 800 gig optics from the vendors shown on the right. So we have 6 vendors today in the lab, and they all talk to each other, of course. These optics are based on 7 nanometer DSPs. So they have a somewhat higher power level than the next generation 5 nanometer DSPs, which are expected to show up in the lab later this year, and are the optics that people want to deploy in volume production next calendar year. And then for breakout applications, it is believed that the vast majority of 800 gig ports will not be used in an 800 gig native mode, even though the 51.2T chip does support 800 gig native Ethernet. But in terms of both the radix required and the installed base of 400 gig, the vast majority of 800 gig almost certainly will be used in either dual 400 gig mode or an octal 100 gig breakout mode connecting to servers in the cluster. And the optical modules can support these breakout applications by using multiple connectors. So we're developing, or the industry, I should say, is developing OSFP modules with dual LC, for customers that want that, or dual mini LC for people who want that, or dual MPO for people who want that, all the way up to an Optical SN connector, and all fits right on the front surface of that OSFP without blocking the airflow. So that's a considerable advantage of being able to break out the 800 gig port capacity into smaller aggregate use cases. Beyond the 100 gig Lambda, the 200 gig is promising at least a 20 to 30% power saving and a similar reduction in cost per bit, which is very, very significant for the cloud, where the cost of optics is one of the biggest investments they're making in the network. And it's obviously the logical choice for the future 200 gig SerDes generation on the switch silicon, which will arrive with the 102.4T silicon in 2025. And the cost reduction is obvious, right? You're going from a solution that's 8 by 100 gig today to 800 gig Lambda optics to 8 by 200 gig SerDes to 8 by 200 gig Lambda optics. It's essentially the same component count. When you open up these modules, they will look basically identical. And the only question is, how much money does it take to repay the NRE to develop all this? But fundamentally, the cost per bit will be significantly lower in the 200 gig Lambda generation. And this, again, the 200 gig Lambda optics will show up sometimes in 2023. It will kick in terms of initial growth in 24 and so on. Each 200 gig Lambda, of course, is the equivalent bandwidth of 200 gig Lambda. So from a bandwidth perspective, the adoption case is somewhat faster. Now, on the pluggable side, the OSFP, which is at 800 gig today in the lab, has a clear shot at the 1.6T generation with 8 by 200 gig electrical interfaces. And the working group that has been working on this since October last year has concluded that this will work just fine in terms of a fully backwards compatible solution. And obviously this is not in production today, but there's no perceived risk to have a pluggable module that's the 1.6 terabit density. And again, these will show up with the Tomahawk, with the 102.4 terabit chip in 2025. Now, as I mentioned earlier, the 200 gig Lambda optics will actually be before the 102.4T silicon. And people do want to deploy this with the 800 gig optics to get to a lower cost per bit. So one question was, is there also a way to get higher density with 200 gig sooner? And in response to customers who were interested in doing this, we developed this thing called the OSFP XD, which is sort of a quad density version. It has dual row connector, meaning 16 electrical lanes, which will support 1.6T with 100 gig SerDes or 3.2 terabits with a 200 gig SerDes. We also up the power capability, and it's still backwards compatible with the OSFP for the existing modules. But what this will allow system vendors to do is to contain a full 15.2 terabit in a 1U chassis, which is quite amazing if you think about that density. This used to be like a full rack, a few years ago. And in the future, perhaps all the way up to a 102.4 terabit in a 1U chassis, assuming this can be cooled. So what's the kind of modules people are looking at for the 1.6 terabit generation is the dual 800 gig CR. Basically, in a 3 nanometer technology, you can just put 2 instances of 800 gig CR in a single chip, and you get 2 channels, which is, I guess, our word for this is CR2, and then the LR2 version, which would be optimized for the 10 kilometer range, but the same silicon. And then for the data center optics, using 200 gig PAM4, either 8 channels or I call it CWM8 here, but what I really meant is sort of a 10 nanometer spacing, so you can capture this in a narrow band without having to resort to thermoelectric coolers, or alternatively dual FR4, which would support 2 800 gig breakouts, or DR8, which would support 8 200 gig breakouts. So it's the same kind of connectors we talked about before, except everything runs at twice the speed. And we do think having the higher channel count is important because it will lower the cost per bit compared to 4-channel modules. There's system cost reductions as well. There's facility cost reductions in terms of reducing the rack space. And we got stuck here again. I'm not sure why this keeps happening. Let's see, this time. Terribly sorry. Here we go. The ongoing advantage, of course, of any pluggable solution is that it can support a wide range of technologies ranging from copper cables to DCI interconnect. And there's this roadmap to 3.2 terabits with 200 gig electrical lanes. So in summary, we do believe increasing the density of optics modules is going to be important to reduce power, to reduce cost, and to enable denser systems. Now, switching topics to the data center interconnect. So this is connecting data centers to each other. This has been very important in the cloud. Microsoft, Amazon, Google, Facebook, they all do this. And 400 gig CR, which is finally shipping now in volume, has been a remarkable success here. This is the first true multi-vendor standard for DWM technology, where there's at least 6 DSP vendors and at least a dozen module vendors in production. And it also matched the density of the client form factor, either in QSFP, DD, or in OSFP, which means that you can plug these things into a regular switch router without losing any density. And it's certainly high volume. This effort started more than 5 years ago when it was proposed as a multi-vendor standard by Microsoft. The OEF began work in 2016. The first silicon was in the lab in 2019. We spent almost a year on interoperability testing, field testing, and this is the first year of volume shipment. And again, this notion of allowing a standard plug, a standard client optics plug to support DWM, the concept has been around for years, but it took the power reduction of the 7 nanometer technology to contain the 400 gig CR module into this form factor, which enables people to deploy IP over DWM natively. This is what this looks like running in an installed base system. 36 ports of 400 gig CR per line card, connecting to each other. You can actually fill up the whole C-band with just 2 line cards. There's a couple of variations, of course, on this. There's the OIF standard application code OX01, 100 kilometer focused data center connect. There's the CR Plus versions, which added additional OSNR improvements and forward error correction to get to further reach. And then there's the Open ROADM one that supports OTN for telco and so on. In the meanwhile, the design teams of these DSP designers already started to work on the Ethernet gig CR design. The basic idea is just to double the baud rate from 60 to 120 gigawatts per second. Stay with the same 16 QAM for easy backwards compatibility, and basically this will drive double the density per module at a much lower cost and power per bit. And we'll have modes that are backwards compatible with 400 gig CR, CR Plus, and will also support advanced 400 gig QPSK, which allows really long reach, like several thousand kilometers with native 400 gig. And then there's the opportunity to solve the campus problem with a further cost-reduced version. Now, the reason this is a very important development is that the 800 gig CR will match the port definition of the next generation routers and switches, which are obviously 800 gig ports. If you can plug in a 400 gig CR into that 800 gig slot, but you would lose half the bandwidth on that slot. And also reducing cost and power, of course, are paramount. There's this ever-going debate: where's the transition point between direct detect, PAM4, and coherent? Historically, it was at the 80 kilometer level. With the 800 gig CR and the 200 gig lambda optics, it's probably around the 10 kilometer level. But there's also going to be use cases for the LR Lite within data centers where there's not enough optics, there's not enough fiber. Now, to compare 800 gig coherent to 4x200 gig, which you can stretch up to 10 kilometers, the PAM4 will be cheaper and will be lower power. So much is clear. But again, you can only have one 4 by 200 gig PAM4 on one fiber. With the coherent one, you can have many channels. So this is the summary from 400 gig CR all the way to 1.6T, which is the dual channel version at 3 nanometer in a single package. The power goes down correspondingly. I did assume that the 1.6 terabit thing here has fixed wavelength instead of tunable. This saves about 5 watts per module. And these modules take 300 gigahertz bandwidth, so you only have 16 SKUs for the whole C-band, which should be manageable. And then, they will come out as a dual LC connector. So each wavelength is really at 800 gig wavelength, and you can route it to different directions. So the summary here is, a clear roadmap ahead all the way up to the dual channel 1.6T density, great reduction in power ahead with 3 nanometer implementations, and important improvements on the performance of this to allow even the longest reaches with 400 gig. But to sum up my talk, and we're getting to the end of it here, overall data center, cloud data center bandwidth, the band growing at least 50% per year. And this kind of thing is true at the chip level in terms of new CPUs, new GPUs. All of them need more bandwidth. At the rack level, you have higher density of chips per rack, and at the data center level. Power has been declining at roughly half that rate. This is true for both the copper and the optics side. So there is, progress has been made on improving that, but more progress needs to be made. Some of the most important areas in my mind are the multi-chip packaging area, 2D, 2.5D, 3D, high-speed yet low-power SerDes area, and we shouldn't bet against the designers there. And anything on the silicon photonics, laser side, the modulator side, that improves reliability, reduces cost, and reduces power. Where does copper end and where does optics begin? It's an age-old question, but arguably it is wherever copper cannot reach. And on a PC board and backplanes, that's going to be like 40 inches or so. On the copper cables, 2-3 meters in the rack, and everything beyond that is going to be optics, which goes from meters to thousands of kilometers. And on co-packaged versus pluggable optics, I think that whole debate was somewhat overhyped in the industry. Both really use these same underlying optics technologies. So the only difference is the packaging. And on the packaging side, the pluggable optics just have clear advantages, which is why 99% of the market is pluggable optics today. So the serviceability, manufacturability, reliability issues still have to be addressed. And most importantly, power has to be reduced. On the pluggable optics roadmap, having a clear roadmap from 800 gig to 1.6T and even 3.2T that matches the silicon density, I think is very important. Having higher channel count will reduce the cost per bit, and economics have always been the biggest driver of new optics form factors. And finally, it is a considerable advantage to be able to support the full range of optics technologies that are being worked on, from DML, EML, all the silicon photonic stuff, lithium niobate, titanium oxide, and so on. So that was the end of my talk, but I think we have some time for questions.
Thank you, Andy. That was an amazing talk, lots of information. We have a bunch of questions that have lined up. Let me start, not necessarily in the sequence that came in. First question from Dan Pitt was, what do you see as the prospect for photonics integration, meaning passive and active on the same substrate, including non-optical components? I'm hearing about power savings of 10x to 100x. Yeah,
so this is where there are power savings, yet the manufacturability of doing this is just really hard. Meaning, if you look at the let me just name one company, which is Intel, which has worked on silicon photonics since I think 2000, and is now one of the leading suppliers of silicon photonic optics transceivers. It took them years and years to get it right, how to embed those lasers right inside the chip to make this a highly manufacturable, and reliable technology. And it has been extremely challenging. I don't know another vendor today, shipping in volume that has fully embedded lasers on a silicon photonics die. most people do assembly, right? Lenses, isolators, maybe 3D printing, whatever's next. But none of these things are really totally integrated. I think when people initially thought about silicon photonics and the promise that it's as scalable as conventional silicon processes, right, where Moore's law has been the fountain of youth of Silicon Valley since 1971, there was this, I think, perhaps incorrect assumption that the same thing applies to silicon photonics. It's a much harder problem because you're dealing with different materials, you're dealing with incompatible processes, and every little problem has to be solved before you can be in volume manufacturing. And people have worked on this for, I don't know how many years, not just Intel, the whole industry, right? DARPA has funded many, many projects along these ways. And it's not yet in sort of predictable near-term volume production. But I'm not saying it won't get there. It's just saying, for the next 2 years, when we have to get products to market, we're going to use pluggables because we know they work. Changing packaging technologies, is nice if it's an improvement, but if it's not required, we can just stay with the way it is without incurring a time to market risk. So again, nobody should slow down developing these new technologies. They will be very important in the future, but we can get to, call it 100 terabit per chip without requiring a further integration between the silicon and the optics.
Got it. Thanks, Andy. Second question from Sissy Wan. Would CPO consider beam forming to reduce loss?
Yes, I mean, everything is important here to reduce losses, right? Because the losses just eat back in the power consumption, all that. And people are working, they're burning the midnight oil, trying to improve these things. I've seen, I don't know how many NDA presentations of every aspect of this that could be improved, and projects funded in the US and Europe and Asia that are all working really, really hard on this. It's not yet in volume production. So when I talked about EBO, which was a slightly different thing, which is a separate issue, which is, the dust sensitivity of single mode fiber is unfortunately so high that the one fundamental challenge here is if you have a switch with 1024 fibers on the front panel, and one dust particle gets into one of these interfaces, either inside the box or outside of the box, and then you have to replace that whole switch, I don't think that's acceptable to the end customer. Whereas with EBO type connectors, where you have the expanding beam, which unfortunately also creates a little bit more loss, but assuming that's manageable, but you avoid the single dust problem, that would be an enabling factor of co-packaging, because then at least you don't have to return the whole switch if there's a dust particle in the field. So that is a hard requirement in my mind. And again, that's not the installed base today. Today, if you have a dust contamination, you send the pluggable optics back, and plug in a new one, and it works, right? And we get the optics back, we look at them, and most of them are no trouble found because they were just dirty. But people, they have a support contract, they send it back and they get a new one. Whereas with co-packaged optics, you can't do that. So this is just a fundamental serviceability issue that the only solution now is expanding beam connectors. But inside the box, the goal is to minimize coupling losses. And one of them is to embed the lasers, but that's really hard.
Yep, got it. Thank you. Question from Shimon. Andy, with emerging 200 gigabits per second per lane Ethernet links, do you still see a role for copper cables, active or passive, in the data center, or is it time to go all optical?
No, that's a very good question. In fact, people are running these simulations right now, and the conclusion is you can go passive copper twin-X at least a meter. With active copper, which is a repeater in the thing, you can easily go 2 to 3 meters. So copper will still work in the rack, and it's likely to be lower cost than optics in the rack. So that actually won't change. On the PC board, you're talking advanced PC board materials, Mectron 8 with 0.90B loss per inch, which is far better than anything before. But with that material, you can also go 10 inches, So you don't necessarily need even flywire cables, depending on the total trace length and the materials involved. So I would not bet against copper at all here. And then there's the flywire cable. So if you can't reach your target with a PC board trace, you can always deploy flywire cables. So the people making flywire cables see a a high volume opportunity for fiber cables ahead here, because it's still far cheaper than optics, right? So people will remain with these copper solutions as long as they can. Now, beyond 200 gig, it gets really hard because you're hitting the FT limit of the transistor technology fundamentally. And, I don't think anybody has a concrete proposal of what's going to happen beyond 200 gig. And you could go coherent, but that's a very power intensive technology. So that's not a good solution either. So we may be stuck at 200 gig at the PAM4 level for a long, long time. But up to 200 gig, PC board traces work, Twinix cable works, copper cables work up to 1 or 2 meters. But beyond that, it's all optics, of course.
Got it. Question from Jay Prakash Balchandran. Does OSFP XD support 16 electrical lanes?
Yes, that's the whole point. So you can do 1.6T with 100 gig and 3.2T with 200 gig lanes.
Yes, awesome. I think Blake answered that question. Another question from Sissy. Andy, can you please comment on what data center will look like with so many progresses of optical connections? How does interconnect tech impact the relationship of server storage switches inside DC? How about WAN?
Yeah, well, that's a much more complicated question. So one thing that's happening there is that people are simply upgrading, right? So they tend to reuse the existing fiber infrastructure, which is perfectly fine, irrespective of the speed. So, historically people had 100 gigabit per lane fiber, or maybe DR4, 4x25. Now they can deploy 400 gig with 4 lanes of 100 gig over that same fiber infrastructure. And with 200 gig lambda, you can do 800 gig 4x200 over the same infrastructure. And there's, nobody wants to touch the fiber if you can help it. And nobody wants to touch the fiber connectors either, because they're perfectly good, right? So having a solution that works with the existing fiber infrastructure is very important. But there's another limitation, which is just power density. So data centers were designed with certain power budgets in mind, certain power per rack, maybe it's 20 kilowatts, whatever it is. But as server power goes up, one thing that happens is you can only accommodate fewer server per rack. So for example, historically a server was, say, 250 watts, or maybe it was 500 watts more recently. You can still put 40 servers into a 20 kilowatt rack. But if the server is suddenly a kilowatt, right, then you have 20 servers a rack. If the server was 2 kilowatts, you have 10 servers a rack. So the number of servers, so even though the size is shrinking, cannot exceed the power budget. And of course, one could do liquid cooled racks, perhaps, that can cool up to 100 kilowatts, but there's a lot of overhead with that. So the installed base of the vast majority of data centers space has been designed around a certain power envelope, which determines what you can put in, and that limits how much density you can actually get. And some of these racks may be half empty. Now the rest of this, it just seems to be scaling quite nicely from the CPU speed today at 50 gig going to 100 gig, next time going to 200 gig in 3 years, to what's available on the PAM4 side, on the switch side, the size of the cluster and the spine switches. So all of this scaling is pretty well lined up. The main challenge, quite frankly, is power. If the power was lower, one could get there sooner. But basically, the industry needs to make the transitions to 5 nanometer and 3 nanometer to get the power down to actually roll these things out. And at least through 25, it seems to be pretty well lined up.
Yeah, yep. For us, it's, we can't cool that much, right? I mean, cooling becomes a problem. We can't populate the rack fully, especially with GPUs and, special purpose ASICs that are coming out. Great, thanks, Andy. Ramon had a question. What type of data center network topologies do you envision for the future with new switches? Still fat trays, or how many ports can you manage?
Well, in the cloud, people have universally adopted the ECMP, equal cost multipath load balancing for redundancy and scaling, and that has worked extremely well. And people have wired in certain radix topologies like 32-way or even 64-way. So nobody wants to change anything. They just want to go faster per link. But what you cannot do is, of course, build a single box that's suddenly 10 petabits. That wouldn't be practical and also wouldn't be reliable. So the leaf spine topologies, which are basically the standard today in any SaaS cloud data center, even enterprise, will be the obvious way how to implement this, and they're well proven from a protocol and deployment perspective.
Awesome. I have one last question here, Andy, from Dr. Sal Hussain. In your list of potential innovation areas, any particular ones more likely to happen sooner than the other?
Well, the silicon transitions are very predictable, right? If anything, I think the surprise was that TSMC and Intel now came up with very aggressive roadmaps. At one point it seemed like Moore's law was stuck at 10 nanometer or 14 nanometer. That was certainly true for Intel, but it was really the extreme ultraviolet process technology. The machines that are made in Europe that enable people to make chips at 7 nanometer and going down to 5 and 3 to 2. Once you cross that boundary, once there was a manufacturing technology that enabled the extreme ultraviolet, Moore's law is back on track essentially. And both TSMC and Samsung and Intel have published roadmaps to 2 nanometer and beyond, right? So in the next few years, in a matter of a few years. So that's actually accelerating suddenly compared to a real slowdown that happened 5 years ago. On the optics side, progress is just a little harder. Optics does not benefit from this extreme ultraviolet at all, right? The silicon photonic optics chips use very traditional 40 nanometer or even less aggressive processes, and they're more worried about integrating incompatible different materials, on the chip, and it's more like a manufacturing challenge how to perfect that. Progress is being made, and there could be a breakthrough, right, that would enable the whole industry to move faster. But it's still, I would say, in the R&D stage, and there's lots of efforts around the world, to advance that. It has been frustrating, I think, to even for the participant to not be able to get it out sooner. But it will happen, right? This is ultimately everything is a question of time until all the issues are resolved. Can I go back to the previous question on the topology?
Yep.
Because there's one other alternative for the, call it the high performance compute world, and some of the AI clusters that look like HPC computers that's running these machine learning kind of payloads. Yep. So many of them are adopting mesh architectures where, like if you look at the Google TPU cluster, they use a whole bunch of copper cables, north, south, left, right, and optics maybe to loop it around to get a 3D torus. But fundamentally, mesh architectures work quite well for AI clusters, HPC clusters, things that run sort of single workloads that are not necessarily even based on IP, Ethernet type technologies. People will do whatever they can to get to the absolute minimum latency, memory transfer kind of approaches for these AI clusters. So that's kind of a separate thing. And even there, people want to stay with copper cables for cost reasons as long as they can. But it's a different network design than the traditional data center, which is based on internet protocols and primarily Ethernet.
Awesome. Thank you, Andy. I think that those are all the questions. Let me just check. Yeah. Thank you. Thank you so much, Andy. That was an amazing talk, a wealth of information. It's we all know how difficult it is to get you, and really want to thank you. If this was a real live presentation, there would have been a great applause for this whole
no. My pleasure. Don't worry.
Yeah. Thank you so much.
Okay.
Really appreciate it.
Thank you. I will stop sharing here.